So hello everyone. So in the last lecture we have discussed about armature reaction. Armature reaction. So it is the what interference, or it is your reaction between your main flux and your armature flux. So let us see how this armature reaction is different in your motor and your alternator or generator. So this is your synchronous alternator, synchronous generator, also known as alternator. Okay, and this is your synchronous motor. So how these are different here. Now in that lecture in the previous lecture we have discussed that for a synchronous generator we have to give magnetic field to this. So this is my north pole and this is my south pole, and we have to rotate this, right? We have to rotate this. So the energy is actually, this is a prime mover. So energy is transferred from this side to this end, right? So mechanical energy is converted to electrical energy. So this is your flux. So this alternator, this rotor rotates and it builds up the flux, and that flux we term it as your phi m. That is your main flux. So first phi m develops, and then the voltage is developed here. That is your terminal voltage. This line to line voltage, and that is called E. Okay, so this is your E, and whenever you are connecting a load here, this is your suppose this is your resistive load in star connection or delta connection. Different types of load will be there. So this is your connection. So this is your load, right? So it can be inductive, it can be resistive, it can be yeah, capacitive, it can be RL load, RC load also. So I haven't discussed RC and RL load there. So this voltage is E, and this voltage, that is your voltage across your terminal, this is V. Okay, so this whole terminology is like this. Okay, so what happens that when you rotate when you rotate the rotor, the flux develop, and this flux makes your induces EMF, and that induces EMF, and that results in the current. This current is IL, and that IL makes your armature, that is phi A. What happens with the synchronous motor case? In motor case, the energy is reversed, right? Energy is coming from your bus bar. This is your bus bar, right? This is your bus bar, and this bus bar will give you the voltage, that the current will flow here, I. This current will flow from here, and there will be, first you will have this, first there will be voltage V, right? And that voltage will create E here, and that E will rotate your magnetic field phi m. Okay, and that phi m interacts with your rotor, and that makes the rotation. So look at the change. The energy is coming from this side, energy is coming from this end to this end, but here it is coming from this end to this end, right? So that is why in phasor diagram, if you draw the phasor diagram, suppose the load is resistive load, R load, and R load is called as UPF, unity power factor, UPF load, UPF load. So what happens if you draw the UPF load for a generator phi m? Phi m will be the main flux that is coming in picture first, and after this phi m comes in picture, after that E will come, that is delayed by 180 degree, sorry, 90-degree E. And this E flows the current IL in the circuit, and this IL is feeding a resistive load. That's why IL will be in phase, right? And this IL will make a current, this IL will make a flux, that is phi A, right? So this is how you are making this is the picture, and that is why this is called as cross magnetizing. Cross magnetizing. Now, suppose the same current is flowing here, and this current is at unity power factor. This current is at flowing at an unity power factor for a motor. For a motor case, what happens that R is, suppose this current is flowing, it is feeding unity power factor. But what happens that first we have V, and that V generates E. So always the E comes first, right? Right. And then we have phi M. This E develops phi M. So 90-degree always phi M. Okay. So main cause of main flux development is E. And this E, as we have unity power factor, the load current will be in phase like this. Or this is your armature current, that is your, here the name changes, this will be armature current. Okay, this is IA, this is your load current. So that is the difference here. So this is armature current will make, okay, now, and this IA will make phi A. So that is your cross magnetizing. Okay, so this is how the things goes on. Now let us see what happens with L load. L means zero power factor lagging, ZPF lagging. Okay, zero power factor. Zero power factor means power factor will be zero. Means the phi is 90-degree. Phi is 90. So power factor cos 90. Cos 90 will be zero. So that is why for inductive load we term as zero power factor lagging load. So what happens with the synchronous generator case? Phi M comes in picture first, and then there will be E here, right? And then this E, because the load is inductive, because the load is inductive, the current will lag E by how much? By 5, right? By IL. Lagging means you have to go anti clockwise direction, na? So it lags E by IL, right? And then what happens with the phi A? This phi A. So this phi A is actually demagnetizing in nature. Demagnetizing in nature. What will happen with motor? Suppose that there is L, that is zero power factor lagging load. Zero power factor lagging load. Now, first E comes in picture. E comes in picture, and then phi M comes in picture, right? This is phi M. After 90-degree, phi M comes in picture. And as the load is as your motor is operating in a zero power factor lagging load, so the armature current will be lagging by E by 90-degree. That is your armature, and this armature will develop a flux, that is phi A. Now here, if you see, phi M and phi A are in the same direction, and that is why it is magnetizing in nature. Magnetizing in nature. So what you find out? You found out that inductive load, for a alternator is having demagnetizing nature. Demagnetizing, it is lessening the main field, while inductive load, under inductive load, feeding a generator, feeding a motor will make magnetizing nature. Okay, so let us discuss for capacitive. So for capacitive it will be, this is phi m. Phi m comes in picture for motor, for generator, and then there will be E, right? For capacitive load, capacitive means zero power factor leading. Again, zero power factor means, because the angle is always 90, whether it is leading or lagging, whether it is inductive load or capacitive load, the power factor will be always 9, the angle between voltage and current will be always 90. But we can specify that for capacitive it current leads, and for inductive current lags. So in the similar position E, here the current leads IL, and this IL will develop phi A, and that phi A makes magnetizing nature. What happens? What happens with this motor? In motor case, E is there, right? E is there. First comes E, and then one after 90 degree there is phi m, right? And what happens with the capacitive C? If it is having capacitive, that means it will lead E. Lead what? E. Lead E by 90 degree. So leading E by 90 degree, that means it will go here. IA. Leading E by 90 degree, that is IA. So here again phi A will be developed, and this phi A has demagnetizing effect here. Demagnetizing nature here. Okay. So if I, let us see what will happen for an RL load. For an RL load, this load is RL. So suppose the power factor is 0.8 power factor. RL load of power 0.8 power factor, and that if it is inductive, so power factor will be lagging, right? So for a generator, E is there. Sorry, for a generator, first come phi m, right? Phi m is there, and then E lags phi m by 90 degree, right? And as the load is inductive, the current lags E by 0.8 power factor. 0.8 power factor, that means it will be like this, IL, right? 0.8. This angle will be 36.66. Cos phi is 0.8, so phi will be 36.86 something. So this is 36.86. Now here there will be two components of the current. If you take, one component will be in this axis and one other component will be in this axis. So this one component is here and one component is here. So this IA has two components. So IA, as you know, this is my phi A, phi A. Phi A is in always phase with IL. So phi A has this armature. I can assure this is a direct axis and this is your quadrature axis. So IAQ. So this direct axis armature has a demagnetizing effect, while quadrature axis has a cross magnetizing effect. So I can say that for RL load, it has both. It has demagnetizing and cross magnetizing. Demagnetizing and cross magnet. Let us see what will happen for the motor case. For a motor case, RL 0.8 power factor lagging. First comes E. After 90 degree there will be phi m, right? And As the load is 0.8 power factor lagging, it will lag E by 90 degree. So this is my IA armature flux, and that is 36.86 this angle. So it has two component. One component will be, and this IA will have armature flux phi A. Again, if you see, one component will be in this direction phi A. You can say this is D and this is Q, phi A Q. So here, if you say phi A D magnetizes your main flux and phi AQ cross magnetizes your main flux. So it can say that magnetizing and cross magnetizing effect. Okay, so this is the whole scenario for both, for your armature reaction, for your alternator and synchronous motor. Okay, this is a very important topic, not only for your exam but also for your gate exams also, competitive. So the people ask you what is the nature. So let us draw one more assignment is there for you to try for yourself. What will happen for RC load having zero 0.8 power factor, leading power factor? Okay, zero 0.8 power factor. So for both synchronous generator and synchronous motor, to try it. Okay, so let us draw one table. Synchronous alternator or synchronous generator or alternator, and one more is synchronous motor. And here one more axis will draw. Let us draw that is your load. Now for our load synchronous generator behaves cross magnetizing. Armature reaction is cross magnetizing. Synchronous motor is also cross magnetizing. For L load means zero power factor lagging. For L load alternators, just check about our alternator how it behaves. For alternator, it behaves as a demagnetizing. For L load, it is demagnetizing, while it is magnetizing for motor load, right? So here we can write it is for demagnetizing for demagnetizing for synchronous alternator, but here magnetizing for C load ZPF leading ZPF leading. It is magnetizing here for alternator and demagnetizing for this. Okay, and zero 0.8 power factor lagging load, that is RL load. For this you have demagnetizing and cross magnetizing, while synchronous motor it has magnetizing and cross magnetizing. And then you find out, I have given you assignment, zero 0.8 power factor leading, that is RC load. Find out what is this. Okay, so if you can find out, this will be asked in your exam, so I will not discuss this now. Why we are doing it? We need to understand that two reference can be made. R load, whatever is R load produces cross magnetizing, while L and C produces magnetizing or demagnetizing, right? So this R load is the real cause for torque production, for torque production in anything, whether it is an alternator for or synchronous motor. Okay, so for the this cross magnetizing is the real nature for torque production. Okay, while this LNC magnetizing or demagnetizing effect is the cause for voltage drop, voltage change. You can say voltage change in synchronous motor or generator. Generally, if it is a demagnetizing, that there is a voltage drop, and if it is a magnetizing, then it is a voltage increase. Okay, so magnetizing effect influence voltage change, cross magnetizing effect influence your torque of a motor. So the whole scenario of your armature reaction is this. Okay, I hope it is clear. So this is one of the important topics of the whole of the syllabus. You must remember, and you must do zero point 0.8 power factor leading RC load. If you understand, you will answer it in the chat box or in the this Google Classroom. Okay, thank you.